All right, guys, welcome to section 3.9. We're still doing our word problems, and we're going to be looking at word problems that have related rates. And we saw a brief introduction to related rates, whether we knew it or not, when we were looking at that problem where we threw a pebble into a pond, and this pebble created ripples, right? And these ripples were moving outward. So this is really representing one ripple. And they're moving outward at a rate of 60 centimeters per second. And we determined this is really the rate of change of the radius. So this is really represented as dr dt. And then what our task was, is we wanted to see how much the area changed as we were going farther and farther out in this circle. Okay. And what we discovered is that the rate that the area was changing was not equal to the rate that the radius was changing. Okay, so we saw that these two rates of change were different. They were related to each other, right, because the area is pi r squared. It involves that radius and that rate of change, but the actual rates themselves were different. All right, so again, we saw that the rates of change were related, right? And they were related with that formula for area, but the rates of change were different. So that's what this section is going to be all about. We're going to be looking at different scenarios where we have two variables that are related to each other somehow, but the rates of change are different. Okay, so more word problems. So our first word problem is number 6 in our textbook. And they're a little bit long, so I still have that PowerPoint. Okay, so here's number 6. So we have that the radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? All right, so notice some key words. We're looking at the rate of one variable, the rate of the radius, and we want to know about the rate of another variable, volume. So this is telling us to use these methods. Okay, so I always recommend drawing a picture first. And I'll write out the steps to tackling these problems in a little bit. So we have a sphere. Okay? And the radius of the sphere is changing. So the sphere is getting bigger. And the rate it's changing is 4 millimeters per second. So every second, this radius right here is going to increase by 4 millimeters. Okay? So that's the first thing I recommend, is drawing a picture and writing out your variables, writing your rates of change as dr dt, and then write what we want to find. And again, we want to find how fast the volume is increasing. So we want to find the rate of change of the volume when the diameter is 80 millimeters. So I would write it like this. So how fast is the volume changing? That's the rate of change. So I'd write dv dt when the diameter is 80 millimeters. All right, and I just want to make everything consistent. Remember, the diameter goes straight across, right? But we've started with radius, so let's just stick with radius. So if the diameter is 80, the radius is half that. So we want to know dv dt when the radius is 40 millimeters. Okay, so this is all the information that problem's given us. So we have to figure out how to find dv dt. So once we've drawn our pictures and we have our variables and we write what we're trying to find, we want to try to find an equation that relates all of these variables. So how does the volume of a sphere relate to the radius? Well, perhaps we remember that the volume of a sphere is 4/3 pi r squared. Okay, so this relates v and it relates r, the radius. So what we're going to do now is we're going to turn v, we're going to focus on the rates of change of the volume and the radius. And how are we going to do that? Well, we're going to take the derivative of both sides with respect to t. Okay, so we're going to get something like this. We're going to get like a dv dt is equal to, and let's see, 4/3 is a constant, pi is a constant. Oh, goodness. Let's do a quick edit. Volume's cubed, right? Area squared, volume is cubed. So let's make that quick edit. And so going back to our problem, the 4/3 and the pi, we can worry about it at the end because they're constants. So we just have to take the derivative with respect to t of r cubed. Okay, and it has to be the chain rule. We have to use the chain rule because r is a function of time. As time increases, r increases. So we have to use the chain rule. So we're going to take the derivative of the outside function first times the derivative of the inside function with respect to t. Okay, so the volume and the radius are both a function of time. Because as time is increasing, the radius is increasing. If the radius increases, the volume increases. All right. So what are we trying to do? That's what we want, right? We wrote that right here. This is what we want. This is our big question mark. This is what we're trying to solve. And we want it when the radius is 40 millimeters. Okay, so that means in this little formula we have, where you can write r squared as what? We can write it as 40 millimeters. Because that's what the problem's asking. We want to find the rate of change of the volume when the radius r is 40 millimeters. All right, and what else do we know? Do we know dr dt? That was given to us in the main problem. It's 4 millimeters per second. I'm just going to write a 4 right there. So we have our dv dt. Let's just simplify this big old expression. Let's see, I'm going to get rid of that 3 because the 3 cancels. And then 4 times 4 is 16. 40 squared is 1600. So if we multiply all of those numbers together, we're going to get 25,600. And then we have pi left over, so we can write in pi. And we can leave it like that if we wanted the exact solution. You can always multiply out by pi using your calculator, and then we get a rounded solution. So those are your squiggle lines. That means approximately. All right, so 25,600 times pi is approximately 80,425. Okay, and then let's talk about units. We could definitely go through and do all of our units in the main problem, but also remember dv dt units, we would consider the units of the volume, and volume is always the cubic unit, so millimeters cubed. Perimeter is millimeters, or distance is millimeters, area is millimeters squared, volume is cubed. And we're looking at that in terms of seconds. So the change of the volume when the radius is 40 millimeters is this number we just calculated, millimeters cubed per second. All right, and there you go. Okay, so these are kind of big problems. So I want to write out some step-by-step approaches just to help us have a roadmap when we approach these problems, because again, they're big problems. So let's talk about the approach to related rates. Okay, so my first hint, well, let's go super basic. We have to read the problem first, right? And we have to recognize that we're talking about two different rates, right? In that last example, we had the rate of the radius, and we were asking about the rate of change of the volume. So we have to realize that we're dealing with two different rates. So reading the problem is important and figuring out those keywords. Always draw a picture. Especially when we have all these variables interacting with each other and we have all these different formulas, drawing a picture is going to be important. And when you draw a picture, let's introduce some notation. Let's introduce some variables. So I'm going to say that as step 3. So in our example, we called the radius r. So that's what I mean by using notations and variables. And then we called the volume v. Okay, sorry about that. All right, and then step 4, once we have all of our variables, let's translate whenever, like any speed that's given or any rates that's given, let's translate that to derivatives. Okay, so we're going to translate the rate to derivatives. And what I like to do at this point, I like to write out what's given. That's like drawing a picture. But then I always like to write out what we're trying to find. So like dv dt when the radius was 40. Okay, and then once you have all of these variables and you know what you have to find, you want to relate the variables together. And how you relate the variables is by writing some sort of equation. Excuse me. Okay. Let's write an equation. Using / relating the variables. So in that previous example, we used the volume formula, right? Volume was related to the radius. Okay, so once we have an equation that relates the variables, remember we're interested in the rates of change. So we would have to take the derivative of both sides with respect to t. So, and we would have to use the chain rule at that point. Because all of those variables, you know, could be a function of time or something like that. So we're going to use the chain rule to find the derivatives. All right, and then at this point, we had to make a substitution with our sphere example because we wanted it when the radius was, or when the radius reached 40 millimeters. So that's your final step, is to make substitutions, make any substitutions to answer the problem. Okay. So let's look at another example. So here we have number 26 from our textbook. A trough is 10 feet long and its ends have the shape of isosceles triangles that are 3 feet across at the top and have a height of 1 foot. If the trough is being filled with water at a rate of 12 feet cubed per minute, how fast is the water level rising when the water is 6 inches deep? Whew. That's a lot of information, right? So again, really important to kind of follow these steps. So we've just read the problem, so we're doing great. And now it's time to draw a picture. And when we're drawing a picture, let's try to use correct notation, and let's use variables as well. And when we're talking about, rates, let's think of them in terms of derivatives. Okay, so we can kind of do 2, 3, and 4 at the same time. Okay, so we're problem number 26. And it's a trough, all right? So what they use to, water the animals on a farm and such. And they said the ends have the shape of an isosceles triangle. So there you go. There's the ends. I'm going to make it a little bit bigger because I know I'm going to have to put in a ton of variables and stuff. So isosceles triangles, 2 sides are equal. And then it's just going to be some kind of long thing. And we're going to fill it with water because we are responsible animal caretakers. Oh my goodness. Okay, so what do we know? They tell us that this isosceles triangle is 3 feet across, okay? And it has a height of 1 foot. I'll try to do that, okay? And what else do we know? We know, so we just did this, but it's 10 feet long, so I'll write that as well. It's 10 feet long. Okay, so those are the dimensions of our trough. And what's happening with that trough? So that's this first sentence. We've done the first sentence. The trough is being filled with water at a rate of 12 feet cubed per minute. That's definitely a rate of change, and it's a rate of change of what? Volume, right? Volume is units cubed. So we have dV dt right here, and we want to know how fast is the water level rising when the water is 6 inches deep. All right, so we're pouring water into our trough. All right, there's our water. And that's going to be a volume. So we're saying dV dt is equal to 12 cubic feet per minute. Okay, there you go. And as our water is being filled up, the height of this water is going to change, right? So I'll just draw it in like this. So the water level is going to rise, and that's what we're interested in. We are interested in the height or the water level. I'm going to just call it H. Why is it doing that? Okay, H. And we are interested, let's read it again, because that's our first step. Read. How fast is the water level rising? So how fast is H changing when the water is 6 inches deep? So in our picture, in our variables that we're using, the water level rising is the change of H with respect to time. And it's going to go, notice because it's not, the volume down here isn't that big, right? Because it's such a tiny little triangle. So H is going to be increasing rapidly. And then as the surface area or the triangle gets bigger, it's going to rise more slowly. Okay. So we want to know what's the change in the height of the water when H is, what did they say, 6 inches? But let's be careful because this is in terms of inches, but everything else we've been writing is in terms of feet. So how many feet is 6 inches? 6 over 12 is half. All right. So there we go. So that's 1, 2, 3, 4 steps in that process. So now we're here at step 5. We want to write an equation using or relating the variables. So how does h correspond with the volume? So how does the height correspond with the volume? Well, the volume, what this water's doing, we can take the area of a triangle and multiply it by the length. That would be the volume of that shape. So let's write that out. The volume of this shape, we would look at the area of a triangle, which is 1/2 base times height. And then we would multiply it by the length of our trough. So it's 1/2, and let's see, this would be considered the base. 1/2 base times height, and the length is set at 2. All right, and then we can clean it up. 10 divided by 2 is 5. So the volume is 5 BH. Okay, so the problem with this right now is we've just introduced a new variable, the base. Do we have any information about the base? Not really. Okay, so what we're going to do right now is we're going to try to get B in terms of H. Okay, so how are we going to do that? Well, notice we haven't used this information, that it's 3 feet across and 1 foot high, our triangle right here. So how we're going to get B in terms of H is we're going to use similar triangles. So let me draw a picture over here. Okay, so it's a side view of the trough. This is 3 feet across, and this is a height of 1 foot. Okay, and then in our little scenario, I'll do it in yellow, we're looking at this triangle, right? We have a base B and we have a height of H. And they're similar triangles because all of the angles are the same. So we have this triangle, the little guy, and then we have the bigger triangle. And they're similar. So we know with similar triangles, we can make ratios, right? The ratios are equal to each other. And we want something for B. So I'm going to put B in the top when I'm making my ratio. So similar triangles have similar ratios. So for instance, we can take the ratio of the bases, and we could say they're equal to the ratios of the heights, something like that. Okay, and H divided by 1 is just H. And then let's do a little cross multiply. So the base in relation to this triangle is 3H. So 5BH is going to become, the volume is going to become 5. B is now 3H. And then times H. So the volume is 15H squared. Okay, so there's our formula relating our two variables that the problem's dealing with, okay? And now remember, this is what we're trying to find, dH dt when the height is 0.5 feet. So we have to use the chain rule to find the derivatives. And remember, both H, the height of the water, and the volume of the water is a function of time, because every minute we're adding 12 cubic feet of water. So the water level will rise and the volume will rise, dependent on time. Okay, so we're going to take the derivative of both sides with respect to t, and we have to use the chain rule for both variables. Okay, so we're looking at dv dt. Okay, and then over here, let's see, h is a function of time. So it's the chain rule. So take the derivative of the outside function first. 2 comes down. What's 15 times 2? Good. Okay, 30h. And now the derivative of the inside function is that dH dt. All right, and now final step is we get to make our substitutions. So what do we know? Again, we're trying to figure out dH dt when h is 0.5. So dv dt is given as 12 cubic feet per minute. So I'll just write 12. H, we want to know what happens when h is 0.5. And then we have our dH dt. Okay, and then this is what we want to solve for. So let's see. This is like 30 divided by 2. Half of 30 is 15. Let's divide both sides by 15. And we get our solution. So dH dt is 12 over 15. You know, you can say 4/5. You can say 0.8, kind of all the same thing. And then let's talk about units. How is the height being measured? Well, distances are measured in terms of feet, right? So this is going to be, or just the single units. This is going to be feet. And again, the time is minute. So dH dt is going to be feet per minute. And then that's your solution. That's the rate of change of the water level when the height is 6 inches. So there you go. All right, let's look at more examples, because all these examples are going to present a new technique. And we're going to number 16 now. So we have that at noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? All right, so again, that's step one, just reading our problem. And look at, we have all of these rates of change, right? Ship A is rate of change is right there. Ship B's rate of change is right here. And how fast is the distance changing? We have to find a rate of change. So that's telling us we're in a rate of change problem. So when we're in a rate of change problem, we draw a picture. Okay, and we have that ship A is a certain distance from ship B at the start of this scenario, right? And we are 150 kilometers away. Okay, and then what happens? Well, ship A starts to travel. And because they're traveling east, right? North, east, southwest. They're traveling east, they're traveling horizontally. So I'm going to call that distance x. And then their speed east will be the change of x with respect to t. Okay, so it's sailing east at 35 kilometers per hour. So the change going east with respect to time is 35. So 35 kilometers per hour. All right, and then ship B is going north. So that's up. And we'll call the distance they travel y since it's vertical. And now their speed, we can think of it as dy dt, is 25 kilometers per hour. Okay, and then what do we have to find? What's the distance? How fast is the distance between the ships changing at 4 p.m.? Okay, so we started at noon and we're going to go all the way to 4 p.m. And the distance between the ships, okay, well, as they travel, let's see. For instance, ship A might be here and ship B might be here. We want to know how that's changing. So I'll call it Z. And what the question is becoming, we want to know dz dt at 4 p.m. So rather than running 4 p.m., let's see how many hours have passed. We started at 12 p.m. And then we're going to go all the way to 4 p.m. to answer our problem. So that's 4 hours. So we want to see how fast that distance between the ships is changing at 4 hours. Okay, so there you go. We have all of our variables, x, y, z, and we got everything in terms of the derivative. And so now our next step is figuring out how everything relates to each other. Okay, so what I notice when we're just traveling north and east like this, that makes this scenario a right triangle. And how do the sides of the right triangle relate to each other? Yeah, we have our Pythagorean theorem. X squared plus y squared equals z squared. Okay? But look, here yellow is z, right? Here in green is y, and then this part in pink is x. But our variable is actually over here. So if this is 150 kilometers and we're traveling x distance this way, what is this pinkish part going to be represented as? 150 minus x. So rather than saying x squared, it's really going to be 150 minus x squared plus y squared equals z squared. All right, so a little bit tricky. Okay, so there you go. We have our variables. We are trying to find a rate of change. This is what we're trying to find. We put a box around it to focus our attention. And we figured out a formula that relates all the variables together. Because we're trying to find a rate of change, our next step is to take the derivative with respect to t of both sides. All right? Because everything's a function as time, right? As the hours pass by, x is going to get closer to b. As the hours pass by, ship A is going to get closer to here. Ship B is going to go farther up, right? And as time passes, Z is going to get longer and longer and longer and longer. So everything's a function of time. So let's go ahead and take the derivative with respect to t. We have to use the chain rule. Okay, so here, let's take the derivative of our outside function. And then we take the derivative of the inside function. Let's see, constant is 0. It's going to be negative dx dt. All right, then plus 2y times dy dt is equal to 2z dz dt. And remember, that's what we want. We want to know the rate of change with respect, we want to figure out dz dt, okay? So let's see, if we wanted to figure this out, look at all the substitutions we need. We need to figure out x. We know dx dt. We have to figure out y. We know dy dt. And we have to figure out z. Okay, so a lot of things. But we're going to use the fact that 4 hours have passed. So 4 hours have passed. How much has our ship A traveled after 4 hours? Well, if we're going 35 kilometers per hour, so after t equals 4 hours, ship A will have traveled, 35 kilometers per hour times 4 hours. Okay, and so that ship is going to have traveled 140 kilometers. And similar situation, ship B is going 25 kilometers per hour. So after 4 hours, they will have traveled 100 kilometers. Okay, so let's draw this triangle. So first of all, let's draw our triangle. This is a right triangle. The height, ship B, will have gone 100 kilometers. Ship A has traveled 150. So what's this side going to be then? 140. So what's this side going to be? Well, if x has gone 140 and this whole distance is 150, 140 plus 10 is that 150, all right? Or 150 minus x. Remember, we got that little formula? So it's going to be 150 minus 140 This little side is 10. Okay, and then that just leaves one final side. Z is equal to the square root of a squared plus b squared by the Pythagorean theorem, right? So z is equal to the square root of, let's see, this is going to be 10,000 plus 100. So 10,100. Okay, so this is the information we need. It happens when t is at 4 hours, and we're going to plug it in to our x, y, and our z. Okay, so let's see what happens. Also, if you guys want, we can also cancel out a 2 as well, but you don't have to. Okay, so let's put everything together. So from this, we're going to get 2 times, again, x is 140. Dang it, I just found a typo. I love it when they can self-correct. When I take the derivative, right, it should be 1. Okay, self-correcting mistake, that's good. Okay, and then times negative dx dt. So the rate of change of x was 35, so we're going to do negative 35. Negative 35. All right, and then plus 2 times y, but y is 100. All right, and the rate of change is 25. And it's equal to 2 times z, but we just calculated z to be this. And then we have dz dt, and that's what we're trying to find, right there. So now we're able to solve this and figure out your dz dt. So, simplify that. And then we can divide out by the coefficient. So check your calculator work. But we should be getting that dz dt is about 21.4. All right, and then what are the units on that? It's a change in distance, right? So it's going to be distance over the time unit. So kilometers per hour. All right, and then that's your final answer. That's your final solution. All right. Let's go ahead and take a quick break, and then we'll come back and we'll do part 2.